Welcome to the Crazy Hat Chemist. So another video here on solubility. So let's get moving. Bam! So today we're talking about solubility example number 7. So if 150 with a decimal milliliters of a 0.11 molar sodium hydroxide is added to 850 milliliters decimal after the zero of a 0.12 molar calcium chloride, will a precipitate form? Again, just like on the previous lecture video that I showed you here, we need to know the formula for sodium hydroxide. Sodium is a group 1, it has a 1+ charge. Hydroxide is a polyatomic ion with a 1- charge. I'm going to put those two things together and I get NaOH, that's sodium hydroxide. Calcium chloride. Calcium is a group 2, it has a 2+ charge. Chloride has a halide ion, that's a 1- charge. I'm going to put those two things together and I get CaCl2. Now, once I mix sodium hydroxide, which is a strong base, so it dissociates 100%, with calcium chloride, which is a salt, which also dissociates 100%, then I'm going to get sodium ions, hydroxide ions, calcium ions, and chloride ions in solution. All of these will have the opportunity to interact with one another. Now, a cation and a cation cannot combine together. Neither can an anion and an anion combine together. That will not happen. A cation and an anion will get together potentially to form a new compound. Okay? Now, already we know that sodium hydroxide being a strong base, if those two things get together, then that will not form an insoluble precipitate. Same with the calcium chloride. As the calcium and the chloride get together, that will not form an insoluble precipitate because that is a salt. So therefore, the sodium, will it combine with the chloride and form an insoluble precipitate? Well, anything with sodium is an aqueous solution. There are no insoluble compounds with sodium, so that is not the answer. So then, it's the calcium and the hydroxide. So the calcium, which is a 2+, group 2, and the hydroxide 1-, that's a 1-, will form calcium hydroxide. That is CaOH in parentheses with a 2 outside. Hydroxides are insoluble except for group 1s and ammonium ions. So therefore, calcium hydroxide is going to be our insoluble precipitate. We're actually going to find out that calcium hydroxide is slightly insoluble, so it kind of depends on what the pH is, whether it's soluble or insoluble, but for this purpose here, this is our insoluble precipitate. So this is why I'm giving you the calcium hydroxide's KSP value of 8.0 times 10 to the -6 at 25 degrees Celsius. You would have had to have looked up this value in the appendix of your textbook or either in the CRC, that is the Handbook of Chemistry and Physics. So, we're going to do a similar thing that we did on the previous problem. We first need to get the concentration of the ions of the sodium hydroxide and the calcium and the chloride, and then we're going to find out the two that combine together, which I've already alluded to verbally. So the sodium hydroxide is not really a salt, but it is a strong base, but it has sodium ion in it, so we call it a salt for our solubility rules. Okay, so we have a 0.11 molar sodium hydroxide solution. It will yield a 0.11 molar sodium ion concentration and a 0.11 molar hydroxide ion concentration. That is, everything here is a 1-to-1 mole ratio. Super simple. Okay. Calcium chloride. Calcium chloride is a 0.12 molar. Okay, the calcium ion and the calcium chloride are in the same mole ratio, so therefore the calcium ion concentration is 0.12 molar. Calcium chloride is a salt, it dissociates 100%. Now the chloride ion concentration is twice that of the calcium chloride ion concentration because the stoichiometric coefficient on the chloride is a 2. But I really don't need to worry about that because my insoluble precipitate right there is calcium hydroxide. So my calcium concentration here is going to be, my hydroxide ion concentration is right here. My calcium concentration is right here. So these two things are going to mix together. Now, I really do need to find out the moles of both and then the volume of both and then the molarity of both so that I can figure out whether or not there's going to be a supersaturated solution and a precipitation, or saturated or unsaturated and not a precipitation. So we're going to write the KSP for the calcium hydroxide. That's products over reactants with the stoichiometric coefficients as exponents. And that's KSP is equal to the calcium ion concentration to the exponent of 1, and then the hydroxide ion concentration with the exponent of a 2. Make sure you note that 2 as the exponent here on the hydroxide. All right, so we're going to calculate the moles of hydroxide ion present. We have a volume, we have a molarity. We're going to take our volume times the conversion to convert to liters, and then using the molarity to convert to moles. So now I have moles of hydroxide ion, which is 0.0055 moles of hydroxide ions. I'm going to calculate the moles of calcium ion present as well. So I'm going to take the volume of the calcium chloride times the molarity with a little bit of conversion with our volume. That's the 850 milliliters times the unit conversion to convert from milliliters to liters, and then times the molarity. That's moles per liter. Okay, you should see that the milliliters, the liters cancel out, and I'm left with moles of calcium ion. That's 0.10 moles of calcium ion. Now, again, just like on the previous problem, when we are mixing these two concentrations of ions, now the volume has increased. So now I need to figure out what the concentration of these ions are in the new volume. So I'm going to calculate the combined volume. Now it's 50 milliliters plus the 850. So 50 milliliters plus the 850, that will yield to 900 milliliters of total solution. So in order to get the concentration of the hydroxide and the calcium ion, I'm going to take the moles of both and divide by the volume total, which is right there. I'm going to convert that milliliters into liters. Super simple. Okay, so I'm going to get that concentration of each of the ions when they are combined. So I'm going to divide by 0.9 liters, 0.9 liters for both. My new hydroxide ion concentration is 0.0061 molar. My new calcium ion concentration is 0.11 molar. Now these two values are going to go into my Q expression, because I don't know if it's the K SP, because I don't know if it's at equilibrium. So this value for the hydroxide is going to go into the hydroxide. This value for the calcium is going to go into the calcium. I am calculating the Q. Now don't forget about that squared term on the hydroxide. I already mentioned that before. So it's 0.11 times the squared value of, the squared value of 0.0061. And that's going to equal 4.1 times 10 to the negative 6. Okay? Now what we're going to do is we're going to compare the Q and the KSP together. So here's my Q that I just calculated, 4.1 times 10 to the negative 6. My KSP is 8.0 times 10 to the negative 6. So they both have the same exponent. So now I'm just looking at the numbers in front of that, at the 4.1 and the 8.0, which one is larger? And in this particular case, the KSP is larger than the Q. So therefore, since the Q is less than the KSP, okay, that is, the KSP is larger, the solution is unsaturated and precipitation will not occur. Remember, precipitation only occurs in supersaturated solutions when the KSP is less than the Q. All right, so now we're not quite done here because we got a lot more here to do. So the question is, what is the necessary sodium hydroxide concentration to begin precipitation of calcium hydroxide by keeping the calcium chloride concentration as it is? That's what we're going to solve for next. Don't forget, donate to my website to get a sticker. Okay, so we're going to keep on going with this problem. That was just a little advertisement break here for you. Bam! So now we're going to answer this question. What is the necessary sodium hydroxide concentration necessary to begin precipitation of calcium hydroxide, yet keeping the calcium chloride concentration as it was before in the previous problem? So in order for precipitation to begin, the reaction quotient, that is the Q, must exceed the solubility product constant, that's the KSP. So, yet maintaining the calcium ion concentration as what we had previously, such that the calculation which solve for the hydroxide ion concentration will equal the sodium hydroxide concentration necessary, because the mole ratio of sodium hydroxide is 1:1. Okay, so we're going to calculate the calcium ion concentration present. That's the 850 milliliters. We got our unit conversion to liters and then our molarity. Okay, we're dividing by our total volume. So this is the same thing that we had before. Okay, here's our KSP expression, the same thing that we had before. Okay, this is going to go into the calcium ion concentration. Now, I was given the KSP, and that is 8.0 times 10 to the negative 6. I have the calcium ion concentration, 0.11. Okay, and now I'm going to solve for the hydroxide ion concentration, so I'm actually solving for x here. So I'm going to divide both sides by the 0.11 and then take the square root, and I'm going to get this value right here. And that's 8.5 times 10 to the negative 3. Then the question is, what is this value exactly? What does this number mean? Okay, so this value, 8.5 times 10 to the negative 3 molar, okay, will give the hydroxide ion concentration necessary for a saturated solution. That's when the Q and the K are equal to each other. However, precipitation does not occur until a supersaturated solution occurs, and that's when the Q is greater than the KSP. So, therefore, any hydroxide ion concentration greater than 8.5 times 10 to the negative 3 molar will give a supersaturated solution and a precipitation. That is, 8.6 times 10 to the negative 3 molar would yield the minimum hydroxide ion concentration necessary to begin precipitation. Any number greater than 8.5, so 8.5, 1 times 10 to the negative 3 would work as well. 8.5000001 times 10 to the negative 3 will work as well. Anything greater than that at equilibrium will work. Okay, I am the Crazy Hat Chemist, and of course we can't end without a crazy hat. This is more like, not quite a crazy hat, but something a little bit different here, so check it out. All right. So, if you like that video, give me a thumbs up. If you like the bell, give me a thumbs up. Subscribe to my YouTube channel, donate, and I'll see you later.